Let us take a look at affine sets. The intuition here is that a set C is said to be affine if a line through any 2 points in C also lies in C. So I'm saying that the entire line that passes through any 2 points in C also lies in C. So obviously C must contain infinite number of points. A mathematical way to say the same thing is that suppose that x1 and x2 are 2 points that belong to C. So for instance, if C is in Rn, then x1, x2 would also be vectors in Rn. Then we are saying that C is affine, and this statement is equivalent to saying that the line passing through x1 and x2, so that line is given by theta times x1 plus 1 minus theta times x2. So this is the set of points that belong to a line that passes through x1 and x2. So this line also belongs to C, right? And this should hold for all theta that are real, right? So notice a few things in this definition. First of all, there is no restriction on theta, so theta can be anything from minus infinity to infinity, right? Which means that all the points that are between x1 and x2 as well as those points that are outside of x1 and x2 are also included. So if you visualize this thing in n-dimensional space, this is the line that passes through them, and this line is described by theta x1 plus 1 minus theta x2, where let's say this is x1, this is x2. Note that when theta is equal to 0, we have this point. So theta equal to 0 corresponds to this point. Likewise, theta equal to 1 corresponds to this point. So let us take a more concrete example of an affine set. So consider the example, the set of all x in Rn such that A times x is equal to b. So I just want to emphasize that here x and b are n-dimensional vectors. Sorry, x is an n-dimensional vector. So x is in Rn, and I am free to choose b. So b can be in, for example, Rm. So A would be in Rm cross n. So is this set affine? Let us try to answer this question. So to answer this question, let us assume that there are two x1, x2 points that belong to this C. So let this be C. So this means what? This means that A times x1 should be equal to b because x1 belongs to C. And likewise, A times x2 is equal to b because x2 also belongs to C. So combining these two, what do we obtain? Let's say that y is the point that lies somewhere on the line between x1 and x2. So y will be of the form theta x1 plus 1 minus theta x2. So what can we say about y? Right, so y is some point like this. Note that theta is a parameter which we are using to describe y. As theta varies over the real line, we get different values of y. So we want to know whether y satisfies this condition and whether y belongs to C. So the question is, does y belong to C? Now to answer this question, we need to check whether ay is equal to b. So we need to check whether ay is equal to b or not. So this is easy to check. We just substitute the definition of y. So we say that y, instead of y, we replace a times theta x1 plus 1 minus theta x2, and this is equal to b. So the question is that whether this is equal to b. But this is indeed the case, as you can see, because the statement here is equivalent to theta times ax1 plus 1 minus theta times ax2, which is equal to theta times b plus 1 minus theta times b, which is equal to b. Hence, we have established that ay is equal to b. And because ay is equal to b, this implies that y belongs to C. And hence, this set that we started out with is affine. So therefore, this set is affine. So in this example, just try to focus on the fact that theta is a parameter. We don't worry about where theta lies. Just worry about where x1, x2 and y belong to for a given value of theta. And there is no restriction. Observe that there is no restriction on theta, but that does not cause any problems here. So theta times ax1 is equal to a times theta x1. Right? So there is no problem here because a times theta x1 is equal to theta times ax1. But this may not always be the case. There may be examples where our attempt to allow arbitrary theta may not succeed, and those sets are not affine. So let us look at another such example. Let's look at the example, the set of all x in Rn such that ax is less than equal to b. I hope everyone is familiar with this notation. This is just a bunch of inequalities. So as I said earlier, this A is a matrix. A is in Rm cross n and B is in Rn. So the Rm. So these are M inequalities. We have already looked at this kind of series of inequalities, all expressed in this compact notation, when we were discussing linear programming. So let's look at what happens if we try to check whether a point y, which is of the form theta times x1 plus 1 minus theta times x2, if we try to check whether ay is less than equal to b or not. Right? So we want to check whether ay is less than equal to b or not. And of course, we are given that ax1 is less than equal to b and ax2 is less than equal to b. So these two things are given because we are assuming that x1, x2 are in C. So this is C. Now to see whether ay is less than equal to b, let us substitute the value of y and we would obtain that theta times ax1 plus 1 minus theta times ax2. Now what can we say about this quantity? What can we say about theta times ax1? And essentially the question is whether this quantity is less than b or not. Whether this quantity is less than b or not. In general, when ax1 is less than equal to b, this does not imply, that theta times ax1 is less than equal to theta times b. So this is not true for arbitrary theta. It is of course true when theta is positive, but we are not allowed to choose theta. Remember, theta is a free parameter which could be any number in the R, right? Theta could be any real number. And because theta is arbitrary, we are not allowed to choose theta, and hence this inequality is not true for arbitrary theta. Now, because this inequality is not true for arbitrary theta, it implies that this inequality is not really true for all theta in R. Right? So this means that it is not necessary. This is not necessary depending on the choice of theta. But remember that in our definition, there was no restrictions on theta. There's no restrictions on theta. Therefore, the definition of affine set is not valid here, which means that this is not true, and this is not true. And in other words, C is not affine. So please try to understand the logic here. In the earlier case, we were able to see that Ay is equal to B regardless of the choice of theta. And in this case, we are able to show that this is true only when theta is positive, which means that this is not true for arbitrary theta, and therefore the definition does not hold, and therefore theta C is not an affine set. So to conclude, we have seen that any point, any sets of the form x times ax equal to b are affine. So for instance, a line is an affine set because line can be described like this. Similarly, a plane is an affine set. So for example, think of a plane. Any line through any 2 points in the plane also lies in that plane, and therefore it is an affine set. But any points of the form ax less than equal to b is not affine. So for instance, line segment is not affine. So line segment is half a line, so that is not affine. Likewise, half spaces are not affine. So what is a half space? It is half of the space. So for example, you take R2 and cut it in half. Draw any line segment, the half of that will be the half space. So that is not an affine set. So just to draw it, this is R2. Let's say this is the XY plane. I draw any line, then this is a half space. And as you can see, this is not affine because I could take 2 points and pass a line through them, and obviously this line lies outside the set. So this is not an affine set. So let us ask the question as to how we can generate affine set. And this question is answered by the definition of the affine hull. So taking a affine hull of a set results in an affine set. So what is a affine hull? So we call it affine hull of a set C is given by summation from I equal to 1 to k theta I xi subject to k greater than equal to 2 xi belongs to C and summation theta I is equal to 1, right? Otherwise theta is a real number. All the thetas are reals, right? So this is the definition of a affine hull. So what really is going on here? We are taking some number of points inside C, then we are adding them up by multiplying them with some coefficients, and those coefficients are real numbers. And remember that we want all of those coefficients to sum up to 1. So even though some of those coefficients can be negative or positive, greater than 1, less than 0, they all should sum up to 1. So that is the definition of a affine hull. In the case of 2, when k is equal to 2, we have to choose theta 1 equal to 1 minus theta 2, because theta 1 plus theta 2 should add up to 1, right? So perhaps that case would be more familiar. So let's take an example for k equal to 2. So k equal to 2, let us consider the set which contains 2 points only, right? So this contains 2 points only. Right, and let's try to find its affine hull. So the affine hull of C is given by, as you can see, we just have to use k equal to 2 here because all k greater than 2 are not really required. There are only 2 points. So we will get all the points of the form theta 2 and 2 theta 2. right? Where theta 1 plus theta 2 add up to 1, and theta 1 and theta 2 are real numbers. So let's simplify this set just to see what it is saying. Essentially, the set is parameterized in terms of theta 2, and theta 1 is not playing any role at all. Whatever theta 2 is, I can always choose theta 1 equal to 1 minus theta 2 and eliminate it. So this set can essentially be written as theta 2, 2 theta 2, where theta 2 is some real number. Right, so I've just eliminated theta 1 because theta 1 is not playing any role. So what kind of set is this? It contains points of the form theta 2 and 2 theta 2 for any real number theta 2. So as you can imagine, this is essentially a line that passes from between 0, 0 and 1, 2. So as you can imagine, this is a line that passes through 0, 0 and 1, 2. And the affine hull of these 2 points is precisely the line that passes through them. So this is another way to interpret the affine hull. What we are doing when taking affine hull is taking any 2 points within a set and then making a line pass through them. And if there are more points within a set, we will make a plane pass through them and so on for arbitrary n. So let's take another example just to clarify the concept. So let's say that this time our set is of the form 0, 1 and 1, 0. So what happens in this case? What is the affine hull? As you can see, the affine hull in this case is given by theta 2, theta 1, where theta 1 plus theta 2 add up to 1 and theta 1, theta 2 are both real. So again, in this case, let us eliminate either theta 1 or theta 2 just so as to get a more compact representation. So what we will do is we will set theta 2 equal to theta and theta 1 equal to 1 minus theta 2, which is equal to 1 minus theta. So we can write it as theta 1 minus theta. So this set contains all points of the form theta 1 minus theta, where theta is a real number. Right, so what is this set? What is the set which contains all points of the form theta 1 minus theta, where theta is a real number? So as in the previous example, this is again a line that passes through the 2 points that we had specified. So we had specified 0, 1 and we had specified 1, 0, and this is again a line that passes through these 2 points. So I hope the idea of affine hull in 2-dimensional case at least is clear. So what happens if we have more than 2 points in a set? So let's take an example where we have more than 2 points in a set. So let's take an example where C has points of the form 0, 1, 1, 0 and 1, 1. So there are 3 points in this set and we want to find out its affine hull. So affine hull of C is given by theta 2 plus theta 3, theta 1 plus theta 3, where theta 1 plus theta 2 plus theta 3 equal to 1 and theta i's are all real. So again, we have just directly applied the definition. And what is this set? So main thing is, what is this set? Let us eliminate one of the theta i's so as to simplify it. So let's say that, so theta 1 plus theta 2 plus theta 3 is equal to 1, and therefore the first point can be written as 1 minus theta 1. Likewise, the second point can be written as 1 minus theta 2, such that theta 1 plus theta 2 plus theta 3 is equal to 1. Now you can imagine that we can eliminate the constraint theta 1 plus theta 2 plus theta 3 equal to 1 because theta 3 is not appearing in the parameterization of the affine hull of C. Right? So if we eliminate theta 3 by taking it equal to 1 minus theta 1 minus theta 2, then this is exactly a set of the form 1 minus theta 1, 1 minus theta 2 such that theta 1, theta 2 are some real numbers. So what is this set? Note that theta 1, theta 2 are arbitrary. Therefore 1 minus theta 1 and 1 minus theta 2 are also arbitrary, which means that the first point spans all the entire real line. Also the second point is also can be an arbitrary point in the real line, and therefore this set, whose first and second points can be some arbitrary real numbers, is precisely R2. Right? This is the xy plane or the two-dimensional plane. So the affine hull of 3 points which were of this form, which were not collinear by the way. So we took 3 points and we have found out that its affine hull is the entire R2 plane. Right? So this is what happens if you take 3 points which are not collinear, which are not along a line, then the entire plane is included. Likewise, you could have taken these 3 points in Rn, and then also there would have been a plane that passes through these 3 points. So this is the general idea of affine sets. I hope the way in which we have described the affine sets is clear. We have described it using the parameterization, using thetas, and those thetas are some parameters which are real numbers. In the same way, we will actually be able to describe all kinds of sets. So this way of writing and this mathematical approach of writing down sets and their affine hulls should be clear.